In this video, I will go over a set of practice problems to help you prepare for your upcoming organic chemistry exam. Problems focus on reactions involving alpha carbon chemistry, organic synthesis, and mechanisms. I will cover key concepts including alpha carbon bromination, alkylation, Aldol condensation, Claisen condensation, and Michael addition. Now let's get down to business. To solve this particular problem, we need to realize that we are reacting a 1,3-dicarbonyl compound with an alkyl halide under basic conditions. So we're going to have alkylation of the 1,3-dicarbonyl compound. So what's going to happen is that the base would deprotonate one of the alpha carbons. Now there are 3 alpha carbons. There's this, and there's this. The alpha carbon with the most acidic proton is this particular alpha carbon. And that's because the conjugate base of that acid, if you were to deprotonate that alpha carbon, that conjugate base could be stabilized by these 2 electron withdrawing groups, making it very acidic. Unlike these other ones, the conjugate base, if you were to deprotonate this alpha carbon, that conjugate base can only be stabilized by 1 electron withdrawing group, making that proton to be less acidic than these protons here. The same thing is applicable to this carbonyl. The same thing is applicable to this alpha carbon as well. So essentially what's going to happen is that the base would deprotonate the alpha carbon, and a negative charge will be placed on this alpha carbon. So we would have this enolate. Now the enolate will attack this carbon and then kick out the bromine leaving group. So the product as a result of this reaction will be such that a new bond is formed between this alpha carbon and the alkyl group of the alkyl halide. So this will be a product. Next question. Since this reaction involved a ketone and an aldehyde, we know we're going to have aldol condensation. So essentially, the base would activate the alpha carbon of the ketone by deprotonating that alpha carbon. And so the alpha carbon would then make a bond with this carbonyl carbon. In the process, the carbonyl oxygen will become an alcohol. So the product from that will be such that a new bond is formed between this alpha carbon and the carbonyl carbon of the benzaldehyde. The carbonyl carbon has an oxygen that will become an alcohol, and this is attached to a benzene ring. So this will be a beta carbon. So we have a beta hydroxy ketone. Now, since there is also heat as part of the reaction condition, we would have dehydration. This simply means that water molecule will be removed from the compound. So 1 hydrogen from the alpha carbon and this hydroxy group on the beta carbon will be eliminated as water molecule. And so a double bond will be formed between the alpha and beta carbons. So our final product would then be this alpha beta unsaturated ketone. So all we have to do is place a double bond between the alpha and beta carbon. To solve this problem, we need to identify the functional group in the reactant. So we have 1 reactant with 2 ester functional groups, and we have a base. Now this tells me that we're going to have Claisen condensation. So we need to identify the nucleophile and the electrophile. Since they're both ester components, just make one of them the nucleophile. Automatically, we will have to make the other one the electrophile. The base will pull off a proton from the alpha carbon of the nucleophile. So if we number this as 1, 2, 3, 4, 5, now that alpha carbon is going to attack the carbonyl carbon of the electrophile. And in the process, the ethoxy group is going to be kicked out. So this will lead to the formation of a 5-membered ring. It's a good practice to number your carbon because it will help you see the number of carbons in the ring you're meant to form. So if we number this as carbon 1, 2, 3, 4, 5, we know that carbon 1 has an ester component. Carbon 5 forms a bond with carbon 1. So this is where the new bond is. And carbon 5 has a carbonyl group. The ester group in carbon 5 has been kicked out. So this is going to be our final product. Solve this problem. Since I have ester as my reactants and I have a base, this tells me that I'm going to have Claisen condensation. So what I will have to do will be to draw 2 molecules of the ester. I'll draw another ester compound here. I'll have to make one of them my nucleophile, and the other one will be the electrophile. So if I make this my nucleophile and this one my electrophile, identify the alpha carbon of the nucleophile. Now a new bond should be made between the alpha carbon of the nucleophile and carbonyl carbon of the electrophile. Eventually, the toxic group will be kicked out as a living group. To draw my product, all I have to do is to redraw the nucleophile here. Then I'll connect the alpha carbon of the nucleophile to the carbonyl carbon of the electrophile. And I'll complete the drawing. So this will be the product of the reaction. Product of this reaction, we need, in predicting the product of this reaction, we need to realize that we have basic conditions and we have excess bromine reacting with the ketone. So this is alpha carbon bromination. Since it's taking place under basic conditions, we have to replace all the alpha hydrogens here with bromine. If this reaction were taking place in an acidic condition, then only one alpha proton will be replaced with the bromine. But in this case, we will have to replace both alpha protons with bromine. And this will be the product of this reaction. This reaction is decarboxylation. Which simply means removal of one carboxylic acid group. So to draw the product of this reaction, all I have to do is to leave one carboxylic acid group on the ring. This is a 3-step reaction. So we have a 1,3-dicarbonyl compound reacting with an alkyl halide under basic condition, followed by hydrolysis under acidic condition, then followed by decarboxylation. So what's going to happen is that the base would deprotonate this alpha carbon and turn it into an enolate. The alpha carbon would then make an SN2 attack on the carbon of the alkyl halide, thereby kicking out the bromine. So this way, The alkyl group of the alkyl halide will then be attached at the alpha position of this 1,3-dicarbonyl compound. In step 2, we would have hydrolysis under acidic condition. What simply happens is that the ester will be converted to carboxylic acid. And in the final step, we have decarboxylation. This simply involves removal of the carboxylic acid group. So my final product then will be this. This question is asking us to predict the starting materials that could be used to make the product. Now, since we know that this is an Aldol reaction, and we have a carbonyl compound here and a hydroxy group, this gives me an idea of what my nucleophile will be and what my electrophile will be. In an Aldol condensation, we know that the nucleophile usually retains its carbonyl group, whereas the carbonyl group of the electrophile will turn into an alcohol. So I'll then identify the alpha carbon on the carbonyl group, and I know that the alpha carbon usually will make a bond with the carbonyl carbon of the electrophile. So this tells me that I have to deconstruct this molecule at this bond. So this means this will be my nucleophile, while this other fragment will be my electrophile. To draw the reactants that will make this product, my nucleophile, I'll just have to redraw this here. The electrophile will have this fragment. However, I know that before the electrophile forms the product, it usually will have a carbonyl group. So I will change that hydroxy group to a carbonyl group. And this will be the answer to this question. To predict the starting material that would form the product, we need to identify the nucleophile as well as the electrophile. We know that the nucleophile usually will retain its ester component in the product, whereas the electrophile will lose its ester component. So this also gives me an idea of what my nucleophile will be. So I will then go ahead to identify the alpha carbon of the nucleophile, and I know that the alpha carbon usually will make a bond with the carbonyl carbon of the electrophile. So if I deconstruct this molecule here, now this is going to be my nucleophile, while this other part will be my electrophile. The answer to this question then would be this. This will be my nucleophile. For my electrophile, since I have this component in the product, all I have to do is to attach an alkoxy group to it. So just give it this ethoxide. And this will be the reactants that will combine together to make this product. To predict the product of this reaction, I need to identify what type of reaction that's going to take place here. And since I have an alpha-beta unsaturated ketone, and I have a 1,3-dicarbonyl compound and a base, this tells me that I will have Michael addition. And in Michael addition, if I were to number, it's always a good practice to number your carbons. So let's number this part. Let's number this part of the electrophile, which is also known as the Michael acceptor. So the base would deprotonate the alpha carbon, and that alpha carbon would then attack carbon 1 of the electrophile. So it will make a bond at that carbon. And in the product, we will have to erase the double bond between carbon 1 and 2. So my final product of this reaction will be such that a new bond is formed between the alpha carbon of this nucleophile and carbon 1 of the electrophile. So if this is carbon 1 and this is carbon 2, now this is going to be carbon 3. Carbon 3 has a carbonyl group, and we have oxygen 4. It's always a good practice to number your carbon. That way, you will not miss your carbon count. To draw the mechanism of this reaction, we need to realize that we have a ketone reacting with an aldehyde. So I'll start by drawing out my ketone. And since this reaction is taking place under acidic condition, it will go through the formation of enol. So the first step of this reaction will be protonation, in which the carbonyl oxygen grabs this proton and we form a protonated ketone. Conjugate base of the acid is formed. Next, we'll have the conjugate base will then grab this alpha proton. A double bond is formed between the alpha carbon and the carbonyl carbon, and eventually this will push the pi electron onto the oxygen, neutralizing the positive charge on the oxygen, and so would form an enol. So this enol is going to be our nucleophile. Since enol is a very weak nucleophile, we need to protonate the electrophile so that we can make the electrophilic carbon or carbonyl carbon to be strongly electrophilic. So we protonate this carbonyl carbon, and this will lead to the formation of a protonated electrophile. The conjugate base of the acid is formed. So this is how I generate my electrophile. Next, I will bring the electrophile here and then react it with the enol nucleophile. Now, since this carbonyl carbon is strongly electrophilic, even a neutral enol can attack it. And it does that by forming a carbonyl compound. So it forms a carbonyl group, and this pi electron would then attack the carbonyl carbon of the electrophile, which will push the pi electron onto the oxygen, thereby neutralizing the positive charge on the oxygen. So a new bond is formed between the alpha carbon of the enol and the carbonyl carbon of the electrophile, and the carbonyl oxygen eventually becomes an alcohol. We need to get rid of the positive charge on the oxygen, so we'll use this conjugate base here. So the conjugate base will be used to deprotonate the oxygen, and our final product will be this beta hydroxy ketone. To draw the mechanism of this reaction, we need to identify the reactants. We have an ester, an excess ester, and then we also have a base. So this tells me that this reaction is Claisen condensation. In Claisen condensation, two esters will react to form a beta-keto ester. And since this reaction is taking place under basic conditions, it's going to go through the formation of enolate. So the base will pull off this proton, and then the bond between the alpha carbon and hydrogen will break, forming a double bond between the alpha carbon and the carbonyl carbon, thereby pushing the pi electron onto the oxygen. Now we have our enolate. The enolate will serve as our nucleophile, which will react with another ester. In this case, this other ester will be the electrophile. So what happens is that the carbonyl oxygen will reform a carbonyl group, which will push this pi electron to then attack this carbonyl carbon of the electrophile, and then pushing the pi electron onto the oxygen. So a new bond is formed between the alpha carbon of the nucleophile and carbonyl carbon of the electrophile. Remember that the carbonyl carbon of the electrophile will form a negatively charged oxygen, which has the ester component as well as a methyl group. Now recall that this counter ion will be attracted to this enolate, and here the counter ion will be attracted to this tetrahedral intermediate. Now, this negatively charged oxygen is going to reform the carbonyl group and then kicks out the toxic group. So ultimately, we would form our final product. The toxic group is attracted to the counter ion. So this would be the mechanism for this reaction. This reaction is simply decarboxylation. I could tell because we have carboxylic acid, aqueous acid, and heat. So what I have to do is to redraw the carboxylic acid in such a way that the acidic proton will be closer to this carbonyl group. So the carbonyl group is going to grab this proton. The bond between the oxygen and hydrogen breaks, forms a double bond between the oxygen and the carbonyl carbon, forcing this bond to break, thereby forming a double bond between this alpha carbon and the carbonyl carbon. This will lead to the formation of an enol. I will also form carbon dioxide. Now, under acidic conditions, the enol will then react with this aqueous acid. The lone pair on the oxygen collapses to form a double bond, thereby pushing this pi electron to grab this proton. Eventually, we need to get rid of the positive charge on the oxygen. And to do that, the conjugate base will go on to grab this proton. There should not be hydrogen here, that's carbon. And the acid is regenerated. So this is the mechanism for decarboxylation. To propose a reasonable synthesis for this transformation, we need to first of all compare a starting material with a product. Notice that this part of the starting material is also present in the product. Additionally, we have two more components in the product, the methyl group and the ethyl group. The way we add ethyl and methyl group is through alkylation. And for us to do the alkylation, also notice that the ester component is not present in the product. So that means we must have removed it. And the way to remove an ester is hydrolysis. So before I would do alkylation, to design this synthesis, I would need to react this ester with another ester to form a 1,3-dicarbonyl compound. Now, this will allow me install the alkyl groups. I will then install those alkyl groups twice because I will install the methyl group followed by the ethyl group. Next, I will then do hydrolysis to convert the ester to carboxylic acid. Then I will do decarboxylation to remove the carboxylic acid group. So that's the strategy to design this synthesis. So to get started, I will react the ester with ethyl acetate. I will have to use a matching base. The base should match the ester. So the product will be such that the base would deprotonate the alpha carbon of this nucleophile, and then this will form a bond with this carbonyl carbon, and eventually the ethoxy group of the electrophile will be kicked out. So my product should be such that a new bond is formed between this alpha carbon and this carbonyl carbon. The carbonyl carbon has a benzene ring. Now that I have my 1,3-dicarbonyl compound, I can go ahead to do alkylation twice. So let's install the methyl group first. So we usually use the base to support this alkylation process. So the base will deprotonate the alpha carbon, and that alpha carbon will make a bond with the methyl group, thereby kicking out the bromine. Now that we've installed the methyl group, we can go ahead and install the ethyl group. Again, I will have my ethyl bromide, then use a base. That base will activate the alpha carbon of the 1,3-dicarbonyl compound, and the ethyl group will be attached at that position. I need to then remove the ester component. To do that, I will have to do hydrolysis. I could do the hydrolysis under acidic conditions or under basic conditions. Next, I will do decarboxylation. Aqueous acid and heat will help me perform the decarboxylation. So my final product then will be I no longer have this group. So my final product will be this. The synthesis of this, to design the synthesis of this reaction, we need to realize that we have new components added. So what I'll have to do would be to react my aldehyde with the ketone so I can form a 1,3-dicarbonyl compound. Do this under acidic conditions. Sorry, under basic conditions. So what the base will do is that it will deprotonate the alpha carbon of the nucleophile, which will then form a bond with the carbonyl carbon of the electrophile. And then this carbonyl oxygen will eventually become an alcohol. Before I will do alkylation, I want to have a 1,3-dicarbonyl compound. So I need to convert this hydroxy group to a carbonyl group. To do that, I could use PCC to oxidize the alcohol to ketone. Now that I have my 1,3-dicarbonyl compound, I can now go ahead and install my alkyl groups. So I have to do this installation twice because we have two different alkyl groups. We have methyl group, so I could use methyl bromide, and the base. The base will activate the alpha carbon by deprotonating the alpha carbon. Then this will be followed by another alkylation using ethyl bromide. So now I'll go ahead and install my alkyl groups on the alpha carbon. And this is the synthesis for this chemical transformation.